All right. So, guys, we are going to, well, here, let me get this fired up and then we'll go. Guys, we are going to start into the next unit. We're going to start into quarter 2. And, guys, so everything that we're going to do from here forward does not go on your first quarter grade. But with that said, let's remind ourselves, tomorrow, 2:45. Can you picture me walking out the door with a smile on my face? That smile is a result of the fact that I know that I will not be receiving any other late work because you will have done all of that and got it to me before 2:45 tomorrow. Can you just picture the glee? 2:45 tomorrow. So very, very happy. Yes. You do want that guy grading your test. Hey, so guys, as we get started, I know that what we did on Tuesday created a little bit of a time gap that has separated you from your Chapter 6 outlines. And so this may not be as fresh on your mind. With that said, I think the question still stands. And the question is this. Guys, relative to chapter number 6, did you notice the hard break? And when I say hard, I don't mean difficult, I mean definitive break. And if you didn't, guys, join me. Starting on page 207, as we start paging through the book, just page by page. So we start with a conversation about waves. And then waves turn to light. And then light turns, page 211, to stairs. Stairs turns to flashlights and spectra and our good friend Niels Bohr, who used to spend significant time with Albert Einstein. Then we turn the page again and holy smack, a bunch of math and Bohr model of the atom. And then we turn the page again, and there's our good buddy on 217, Heisenberg, who created what we call the uncertainty principle. Hey, and then we turn the page again, and now we're back to waves. But now these waves aren't light. Now these waves are strings representative of particles. And then we turn the page again, and oh my goodness, now all of a sudden we got clouds. And these clouds continue on, and then the clouds on 223 turns into humps on graphs, and then we get to the bottom of page 223, and the humps on graphs turn into spheres. On 225, they turn into what we call dumbbells, and the next thing we know on 226, now this starts to feel familiar. Because if you take a second and look to the east, it's this stuff. Ethan. So guys, now we've got this stuff, right? And we've got the stuff that we talked about last year. And 227, we've got spinning electrons. And 229, we've got 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. And we've got orbital filling diagrams. And then we relate that on 233 to the periodic table, and we've got the S and the P and the D and the F sublevels on our periodic tables, and then, oh my gosh, the chapter's over. But guys, here's my question. Picture what you learned last year, right? Because this, right, last year. Here's my question. On what page, and I want an answer, on what page did we insert ourselves last year into this material? Find a page. Okay, so I'm hearing some suggestions on 220. So here on 220, we've got energy level, sublevel, orbital stuff. We've got clouds. We've got probabilities, which is a fascinating idea. Does anybody want to go earlier than 220? Okay, so maybe, and Kaylee, I was there as well. So maybe 214. So we did talk about Bohr, but guys, if we remove Bohr from the picture, and then if we turn to the right, I would suggest to you guys that somewhere maybe between 214 and 220. But let's just go the deepest we can, 214. Guys, what do you see to the left of 214? Light and waves and stairs and photons and energy and all of this stuff. So, and the electromagnetics. So guys, this then becomes the question. You already know the end of the story, because the end of the story is all of this glorious stuff that you learned last year. But the question is, why on earth would a chapter that ends up here start, let's go all the way back to the beginning, page 207. Guys, why would a chapter that ends up here begin with this interesting picture about neon lights? So, guys, what's the connection? And Brisha, I'm sure you're doing something important, but make sure you catch this connection. Guys, what's the connection? Why would a chapter about electrons begin with neon lights? Do you make the connection? What's the connection, Cherry? I see you nodding, so forgive me for calling you out, but yeah. So a flow of electrons is electricity. That's true. So there's a connection there. But guys, where we're headed with this is electron structure, right? So what's the connection? Why would we study light if we want to learn about electron structure? Isaac? Mm-hmm. Yeah. 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 And so let's do this. So guys, this is from your homework last year. Obviously don't write any of this down. But here's the question I have for you. Where in, and you understand that these are in, is it chronologic or chronological? I don't know. They're in order by date. So guys, this is earliest, this is latest, this is most recent. So guys, here's my question. Let's just number them 1, 2, 3, 4, and 5. Where do you start to see order in the atom? Well, we see a little bit of order in 2 and 3, but where do we see order that begins to suggest the things that we currently understand about atoms? I would agree with 4. So guys, this is then the question. Who was it that suggested this order? And the answer is Niels Bohr. And then the question is, how or what did Bohr do? And Isaac, this is to your observation. Guys, what did Bohr do in order to get this idea that the electrons, unlike the Rutherford model, what did Bohr do in order to figure out that these electrons are actually organized into what he thought were like orbits, and Schrodinger later suggested were like clouds? But guys, what did he do? And the answer is he studied light. And so what is the connection between light and the organization of electrons? And guys, the answer is really interesting. And it does have to do with the stairs. You can tell I wasn't planning on doing this. So guys, this is what Bohr did. This is what you're going to do in lab next week. So guys, what Bohr did, so we're looking at about 3,000 volts here, so we're going to be really careful with this. But what Bohr did is this. He took samples of atoms. And remember that Bohr, at this time, was building on the research of Rutherford. We knew that there was a nucleus, but the present thinking at this time was that the electrons were just in the plum pudding. They were just this diffuse area of electrons like plums in pudding. And then what Bohr did, which was brilliant, was he took some of these elements and he passed a current through them. How did we do this last year? We didn't use current. What did we use? Remember? The flame test lab? Do you remember that? And we talked about the idea that we can discern how far electrons are falling based upon the color of light that they emit. Roy G. Biv, red is low energy short falls, violet is long energy high falls. And guys, we used heat to excite electrons. And when these electrons excite, let's make sure you remember the terms. What do we call the low energy state? Ground state. What do we call the high energy state? Excited state. They can't stay there. They are not supported, if you will, in those excited states, and they return back to their ground state. Now, energy went in to excite them. We used heat. Just a second. We used heat. But then, guys, when that energy is re-radiated, it is re-radiated in the form of light. Last year, we did this, forgive the term, but it's the right one, grossly. We just looked for the overall color. What we're going to be doing in class, in lab this year, is we are actually going to be passing this light through a spectrum. And what you will find is the light that appears to us to maybe be a yellowish, orangish tinge is actually made up of many times dozens of different colors. And our brain collects all of that information and mushes it together into one color that we call whatever you would describe that. But guys, if you take that light and pass it through a prism, you will actually see the bands that make up all those different colors. Now guys, what do those bands represent? And the answer is falling electrons. But maybe we have one that's falling, maybe from energy level 6 down to 1. That's going to be a very violet colored light because it's a long fall. Maybe we have one that's going from 3 to 2. Shorter fall, redder light. And we pull all those things together and that gives us a sense of this overall color. But when we break it apart, guys, we can gain information about the individual electrons. We're going to be doing that in lab next week. So guys, the idea then becomes this. I asked the question previously, why do we study light if we want to know about electrons? Guys, the answer to that question is, where does light come from? Where does light come from? There's only one answer. Where does light come from? Falling electrons. Guys, light comes from falling electrons. So how does this work? Well, guys, the idea here is that the electrons want to be in their ground states. When we excite them, they go to excited states, and when they fall back down, they re-radiate that energy as light. You guys understand that? Okay, so that's the fundamental idea, is that because light is the result of electrons losing energy, we can use that energy in order to study electrons. Do you see the connection between the two? So guys, this is the... Oh, shoot. Would you do me a huge favor? Would you mind taking that down to Miss Harward instead? She's going to be really glad to see that. Thank you. And so, guys, back to the idea then. So we study light because it gives us information about electrons. The problem is we haven't done that yet. right? We talked a little bit about Roy G. Biv and red being short, low energy, and violet being high energy. But guys, we're going to do a much deeper dive on this today. So today we are going to talk about the things that you need to understand about waves in order to then make the connection in order to go there. So guys, do you understand what we're doing today? Okay, so in order to get started then, let's answer the question that we just posed generically. And if you don't understand the answer, guys, I'd encourage you to sort of scratch this down. So why do we study light when we want to study electrons? And guys, the answer is that much of the information that we understand about electron structure comes from the study of light. And so that then becomes our connecting idea, if you will. So what we're going to do today, guys, is we are going to study light, and then we'll bring the electron piece into it in just a minute. Well, actually, next time. So, and I'm realizing I didn't print my notes, so I'm going to do that while you guys are writing this down if you want, and then we'll get going. So guys, at this point, I have to ask the question, how many of you have not taken physics? Okay, a few of you, and that's totally fine. So guys, for those of you that have taken physics, you're probably, and even if you haven't, you're probably familiar with the idea of wavelength, frequency, amplitude. We're going to talk about those things, but we'll get into them. If you've taken physics, they'll be familiar. If you haven't, you'll be just fine. So you guys ready to go? You ready to dig into this? All right. So here we go. So guys, as we move forward then, the idea then becomes this. As we now talk about light, the first thing that you need to understand is that light is a form of what we call electromagnetic radiation. So let's break that down. So what does it mean that it's electromagnetic? And guys, we don't do a deep dive on this in here. If you do choose to get deeper into chemistry or especially physics, you actually tease the electrical and the magnetic components of this apart. But in here, we don't need to do that. But guys, radiation, electromagnetic radiation, does have an electric component, but it also has a magnetic component. The thing that you need to know is this. When we talk about electromagnetic radiation, you simply need to know that it's a form of energy that has wave-like characteristics and it can travel through a vacuum. And you guys understand that a vacuum is just the absence of matter, right? So guys, what that means then is that light is self-transmitting. Sound in a vacuum, you got nothing, because sound has to travel through air or some other medium. It's a wave of energy through a medium, whether it's air or the desk or whatever. But guys, light does not need something to transmit it. It travels through empty space. It propagates itself, so it can travel through a vacuum. So you guys ready for a deep thought? How fast does it go through a vacuum? The speed of light. So guys, ready? Light travels at the speed of light. I know. You think that's deep. This is the value for the speed of light. Isaac, that's becoming distracting. Yeah, thank you. There you go. So you guys ready? Okay, you have a choice. Do you want today to just be quick and dirty and to the point? Or can we get nerdy? Because there's all sorts of interesting nerdy stuff that we can talk about as we're going over this. But I also appreciate that it's the end of the quarter. Some of you right now are so sleep deprived and malnourished that you're barely vertical. And so guys, if you're just like, give it to me straight, let's get through this, we can do that. Or if you want to get nerdy and talk about interesting things, we can do that too. But I don't want to beat you with information. So you tell me, are we quick and dirty, or are we nerdy and more entertaining? Nerdy? You want to get nerdy? All right, so you ready for nerdy? Guys, we actually don't know that this is the speed of light. So let's talk about this. So the question becomes this: how do you measure the speed of something? So guys, imagine that we're running a 100-meter dash, okay? Can you picture it? So at one end of the track are the starting blocks, and at the other end of the track, if we're doing this right, there's a photo gate, and when the athletes run through the photo gate, the clock stops, right? But how does that work? How does the starting blocks and the photo gate actually measure how long it takes for the runner to run? You ever thought about it? There has to be a wire, or there has to be a way for the clock that's sitting at the finish line to know when the starter hit the gun, right? So boom, and there's actually, do you guys know how this works? There's actually a microphone down there at the finishing line, and it hears the starting gun and it starts the clock. Does that make sense? So when the boom and the gun goes off, sound transfers information. That information then starts the clock, and then when the runners break the thing, then we know how long it took them to get there, right? Do you see the problem with that? It takes an instantaneous portion of a second for the sound to get from the gun to the starting line. So that time is actually not completely, you just got to let me go, Isaac. So the time is not completely accurate because that information has to travel. Do you understand what I'm saying? So guys, how could we make it better? The answer is use a wire. We could actually run a wire from the starting gun to the finish line, and now that information is not traveling at the speed of sound, it's actually traveling at the speed of electricity, which is pushing the speed of light. And so that information travels through the wire, and now the delay between when the gun went off and when the timer knows the gun should have started is much shorter. Do you get the idea? So here's the question. How do we measure the speed of light? Do you see the problem? Because guys, the problem is this. If we want to know the speed of light, we need a finish line and we need a starting line. And we're going to get light to go this distance. But what has to happen is the finish line needs to know when the starting line sent the light. Isaac, I'm not doing questions and I'm not doing comments. So guys, do you see the idea here? That the problem is if this is the starting line and if that's the finishing line needs to know when the light left so it can figure out the time it took to get there. But do you see the problem? How do we get that information there? Best case is electricity, which is traveling the speed of light. Get the problem? So how do we fix it? And Isaac, I'd love to know if you know the answer, but you got to stay on topic with me. How do we fix the problem? And that's what we do. We put a mirror right here. And then what we do is the starting line and the finishing line are now the same place. Get it? So now we know how long it took the light to do this. But guys, now we've got a problem. And this sounds stupid, but this is actually a problem. Here's then the problem. We are not measuring the speed of light. We are measuring the speed at which light goes there and back. And this is not bunk. This is really a problem. Look it up. There is the probability that it takes light some amount of time to get that far, and then it returns instantaneously. And there's no way for us to prove that that's not what is actually happening. Look this up. It's great. Told you nerdy, right? But guys, we actually don't know for certain the speed of light. All that we know is the speed at which light makes a round trip. And there's the possibility that those speeds are different, that it could go out at one speed and back at another speed. And we can't for sure distinguish whether or not that's happening. And the implications of this are crazy. We're not going to get into them. But was that too nerdy for you? Do you find that interesting? I find that, I don't care if you do, I find it interesting, yeah. Perhaps, but then you can never, so this is, you can never measure the direct path speed of light. You can bounce it around all you want. You can break it into smaller and smaller paths, but you can never measure the direct path speed of light. And it's interesting because if in fact light is doing this and going out over time and returning instantaneously, all of Einstein's equations with relativity completely change. Yeah, it's really, anyway, too nerdy? Just right on nerdy? Just right. All right. So, guys, anyway, and look this up if you'd like. There's fascinating videos on YouTube about it. So, regardless, guys, this is then where we need to go with this next. Understand that light is not the only type of electromagnetic radiation. And we should know that because we know that there are different colors of light. Red, orange, green. You guys know, do you guys know the colors of the rainbow? Do you need to write them down? Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Just Roy G. Biv. But guys, it doesn't stop there. This is what is called the electromagnetic spectrum. And guys, you'll notice that visible light is right in the middle of it. In my little world, I don't think that's a coincidence, but we can keep talking. So, guys, radio waves. Some of us still actually listen to the radio in our cars. And guys, if you're listening to a radio, somewhere out there in the valley, there's actually a tower that is sending out information over electromagnetic waves. But guys, here's the thing that's interesting about that. I want my writing utensils. And so, guys, the thing that's interesting about that is that these waves actually, not only do they carry information, let me see if I can draw. There we go. Not only are they carrying information, but guys, the waves that carry this information, and these are in meters, guys, these waves are on the order of the height of a building. So they're somewhere between like 1 and 100 meters. So if you could see the energy coming off the KOHS tower, those waves would be between a meter long and like a football field long. So these are long. This is long wavelength energy. So guys, what happens when you change the channel from one wavelength to the other? Well, I just told you. When you change the channel on your radio, you're actually switching between wavelengths. And so what is KOHS? I don't even know. Do you guys even listen to it? 91.7. Guys, that's not the wavelength, that's actually the frequency, and we'll relate them, but they are related. So when you tune your radio to KOHS, you are tuning your radio to one particular wavelength of energy, and then you can just keep switching from there to other wavelengths. Then, guys, we get shorter wavelengths like microwaves. Microwaves have a wavelength on the order of a grain of sugar. So much, much shorter wavelength energy. Guys, the thing that's interesting is this. In between these is where cell phones and Wi-Fi live. And so in between those is where we have all of the ways that we transfer information for computers, which is why, if you've ever noticed that if you turn on your microwave, sometimes your computer slows down, it's actually because there can be interference between your microwave and your Wi-Fi. No, exactly, because Bluetooth as well. So everything that you have that's Bluetooth can be in there as well. So here's an interesting question. Guys, how is it that we organize all this? Because there's only a fixed number of wavelengths, right? So how is it we organize this so that when you hit your microwave, it doesn't blank out all of your computers when they're connected to the internet? Because the answer is there's an organization here called the FCC, the Federal Communication Commission, and they own all of these wavelengths and they sell them for profit. And so if you want to build a brand new cell phone technology that isn't the same that Verizon and AT&T use, because those are different, then what you end up having to do is go to the FCC and say, I would like to buy a part of the electromagnetic spectrum that I want to use to do a brand new cell phone thing. And guys, we are talking about millions and millions of dollars to buy these parts of the spectrum, but the government owns them all. Yeah. What's that? Oh, between countries, many times they don't. So, for example, with our cell phones, if you're on... Exactly. So if you're on AT&T or T-Mobile, they are actually on a standard that's more global. But if you're on a Verizon phone, they actually, for a long time, didn't work in Europe because Europe is on a different standard. What they're doing now is they're putting both radios in all the phones. So you can use the same phone on AT&T or on Verizon. That used to not be the case. Isn't that interesting? But then that's a great question. So countries come into compacts. What are you showing me?
This is actually, there are two different regions and this is divided.
Around the world?
Yeah.
Oh, there you go. So apparently they have entered into compacts. But again, within our borders, we sell this for profit. Isn't that crazy? So guys, then moving on again, we're down here into the infrared range. That's the red light that keeps your McDonald's hamburger warm between the time that they cooked it and the time that you pick it up. Those are red heat lights. Then guys, we understand that here we've got visible light. Then we've got ultraviolet light. Now guys, notice this. Ultraviolet light is the light that causes sunburn and also the light that causes cancer. How long is the wavelength of ultraviolet light? On the order of the size of molecules. Doesn't it then make sense that ultraviolet light mucks with our molecules and causes cancer? Huh? Right. Then, guys, we've got X-rays, and these are the X-rays that we use in order to take like X-rays of our teeth. And, guys, those are on the order of the size of atoms. And then we go all the way out to gamma rays, which are on the order of the size of atomic nuclei. Right? So, guys, we're going from the size of like football fields all the way down to the size of atomic nuclei. And all of these are electromagnetic radiation. They all travel the speed of light. The only difference is the size of their waves. You get the idea? Can we do one more nerdy thing or should we go on? Okay, how do they make X-rays? This is fascinating. I actually, when I was at the dentist a couple months ago, and while they left me alone in the room, which is never a good idea, I actually got up and grabbed the X-ray machine and started looking at it and shooting pictures. And it's really cool what they do. They actually take tungsten atoms, right off the periodic table. They take tungsten atoms, if I can draw a picture. So the nucleus of a tungsten atom, right? And we've got the electrons, sorry, I ran out of space, but we got the orbits around there, right? And what they do is they take these tungsten atoms and they blast them with thousands and thousands of volts of energy. And when they do, remember these are the energy levels, right? Full of electrons. What happens is if I draw in a couple electrons, they hit the tungsten with so much electricity that these inner core electrons actually leave. They hit them with so much energy that they ionize and go away. And then what happens is this. These electrons that are out here actually fall down to replace them. And when they do, the fall is so long that it releases X-rays. Isn't that cool? That's actually how they do it. They super excite tungsten and it ejects core electrons. And now there's an open space in the basement, if you will, and all these electrons that are out in these higher energy levels fall in to replace them, and that releases energy on the order of X-rays. Isn't that cool? Never leave me alone at the dentist. But I find that interesting. So, you guys good on these ideas? And so we've got this idea of electromagnetic radiation, all sorts of different wavelengths. Good? Okay. Now, guys, watch this because this could be confusing. Which end, left or right, is higher energy? Left or right? The right side is higher energy, and let's relate that. Remember what we said before last year in class, just talking about Roy G. Biv, we said red is long wavelength, low energy light, violet is short energy, short wavelength, high energy light. So this is high over here, this is low over here. Good? Evan? Yeah. Uh-huh. Brilliant. Can we talk about it? So how do microwaves work? And the answer is actually really interesting. So imagine that you're warming up a cup of water in the microwave. And so what happens is these microwaves that have wavelengths on the order of like a grain of what does it say, sugar, whatever, doesn't matter. It turns out that those microwaves have a wavelength that interestingly interacts with water molecules. So microwaves don't pass through water cleanly. And when microwaves pass through water, it literally causes the water molecules to vibrate. And when they vibrate, they rub up against each other, and that friction causes heat. And so the bottom line is if you put something dehydrated in a microwave, the microwave can't warm it up. Because it's actually not warming the food, it's vibrating the water in the food, and all those vibrations heat up everything around it because of friction. And so that's how microwaves work. So you're right that they are relatively low energy, which is why you got to put things in there for minutes on end. But all they're doing is making water molecules vibrate. Yeah. That's a whole different deal, and it actually has to do you have Ellingford for English? Shoot. Ellingford has this really, really strange fascination with trying to take, it's called a magnetron, it's the gun that creates the microwaves, and trying to turn them into weapons. So if you have Ellingford, talk with him about magnetrons and microwaves, and he gets weirdly excited. But it has to do with the grounding of the case of the thing and the way this energy, it's bigger than that, but it doesn't have to do with the same thing that causes and there are even now microwaves that are set up properly so that you can put metal in them. Like the microwave that we have actually has a metal rack in it. We don't use it, but you can, and the way that it's grounded, it all works. But it's a whole different deal. So guys, you good on these ideas? Okay, now don't miss this because this could be misleading. So guys, watch carefully. Which side is high energy, right or left? Right. Now watch. See the change? Now where is it? Yeah, so it flipped. Don't miss that. But guys, why am I now presenting you with another image of something that we just talked about? And guys, the reason is this. We talked already about wavelength. That radio frequencies are on the order of maybe a meter to a kilometer, football field, 100 meters. And then down here with gamma rays, we're talking about a wavelength on the order of the size of the nucleus of an atom. Because the reason that I bring this up is there's a related idea that you also need to understand, which is frequency. Frequency and wavelength are the two important descriptors that you need to understand when it comes to waves. And so guys, if you can picture wavelength, it's literally the distance between two repeated points on a wave. Frequency is a little more obscure because it requires a video rather than a drawing. So guys, if you want to picture frequency, the place my mind goes is this: ocean waves. And imagine that you're sitting on a beach and you're watching the waves come in, and then you start a stopwatch and you start timing the waves. 1, 2, 3, and you count 20 in a minute. Well, guys, that's then the frequency of those ocean waves. It's 20, we call them cycles, 20 events or cycles per minute. The difference with this is that minutes are way too long, and so instead we measure frequency not in terms of minutes, but in terms of seconds. So here's what that means. If we're down here on the order of radio waves, which are like a football field long, guys, we're looking at about 10,000 waves per second, which is still hard to wrap your head around. But guys, the KOHS tower is spitting out waves at a frequency of about 10,000 per second. So we've got long wavelengths, but we've got low frequency. Guys, down here where we're talking about gamma rays, high energy, short wavelength, guys, look at how many waves we experience per second. It's not Avogadro's number, but it's not too far away. Well, it's still far away, but it's a big number. So guys, the idea is this. What then is the relationship between frequency and wavelength? Is it direct or inverse? It's inverse. The shorter the wavelength, the smaller the wavelength number, the higher the frequency number. The bigger the wavelength number, the bigger the wavelength number, the shorter the frequency number. You sold on that? Okay, so guys, let's pull these together then, because we need to talk about those relationships. So guys, don't draw this if you don't need to. Do you understand wavelength? Do you understand frequency, which is really not represented here, but you're picturing ocean waves? Many times then people will ask about amplitude. Guys, we do not need to include amplitude in this conversation. Don't worry about it. But we do need to worry about this, and this you need to get in your notes. Guys, waves are described by two factors. You already know them, frequency and wavelength. Because we need to talk about these individually. So first of all, wavelength. Wavelength is abbreviated by the Greek lowercase letter lambda. If you're curious, uppercase lambda looks like this. But this is lowercase lambda, and guys, I do it like that. Technically, it's got a little crossy thingy on it, but this is lowercase lambda. Find it on your AP equation sheet. Guys, make sure that you can identify quickly lambda. You got it there? So guys, what then are the units for lambda? And the answer is the units are measured in units of length. Which for our purposes will be meters. Now frequency. Guys, frequency is the other bit of information we need to keep track of. Please notice, however, that the abbreviation for it looks frighteningly like the letter V. That is not the letter V. This is actually the Greek letter nu. Interestingly, capital nu, capital nu is where we get our N's. So actually the capital Greek letter nu is an N. But lowercase nu is like a sexy V. Sexy little v. But guys, your child, find it on the AP equation sheet so that you know what it looks like. You got it? Then guys, this. The units for nu, what is nu, what does frequency represent? It's the number, we'll say crest. It could just be repeated points, however you do it. It's the number of crests that pass a fixed point in a second. So then, guys, the question becomes, what are the units? And the answer is hertz. H-E-R-T-Z. But guys, notice the way that we write those units. It's seconds to the -1. It's things per second. So now when you go out to buy a computer and there's a tag on there that says that this has got a 2.5 gigahertz processor, you now know what that means. Giga is billion, and so that means that your computer has a little clock inside there that's spinning at 2.5 billion cycles per second. It's more complicated than that, but really that's when we talk about the speeds of computers and things like that, it's measured in gigahertz, which is the number of things that this thing can do per second. It's the speed at which it can think. And again, it's in not hertz, but in gigahertz. So, guys, you good on this? Wavelength, frequency? Okay, so now what we're going to do quite literally is we're going to bring them together. And this is where this gets interesting. So what happens when we bring frequency and wavelength together? And the answer is we get speed. Do you see it? Do you see it? Do you? Yeah? Guys, if you don't see it, do this. This is frequency. This is wavelength. What are the units for frequency? Or I'm sorry, what are the units for wavelength? What do we measure wavelengths in? Meters. What are the units for frequency? Inverse seconds, which means 1 over seconds. Seconds to the -1 means put it in the denominator. What happens when you mush these together? You get meters per second, which is speed. But guys, if our waves are electromagnetic radiation, what do we know the speed is? The speed of light. And as a result, all of a sudden, this equation makes sense. C is equal to lambda nu. Because you know, if nothing else, from our good friend Einstein, E equals mc squared, C is the abbreviation for the speed of light. Find this on the AP equation sheet. Are you guys good? Yeah? You guys all find it? Okay. And you see the value for C off to, is it on the right? Yeah, the value for C on the right. Meters per second. So guys, using that information, solve this question. You've got about a minute. Write down your equation first and then solve it. Actually, hold on. Let's set the stage. So guys, one of the things that I love the most about Utah County, and maybe you don't know this, but there's a rule. It says everywhere there's a school, elementary, there's got to be a park. Do you guys know that? Every elementary school in Utah County has a park next to it. That's not a coincidence. But guys, if you can imagine going into one of these city parks, many times they have a big old area of like concrete or asphalt with basketball hoops. And then many times they took the time to put the lights up there so you can play at night. And can you picture what those lights look like? They're those big aluminum bells that are hung upside down with those weird like light, like the glass that goes around them that's all striated so it diffuses the light. But have you ever looked at those lights and have you noticed that there's a weird yellow color to them? You know what I'm talking about? It's because they're what are called sodium vapor lamps. You may remember last year from the flame test lab that when you flame test for sodium, it flame tested yellow. That's why. Guys, when electrons in sodium are excited and then return to their ground state, the predominant color that's released is actually yellow. And whether you excite that with heat or electricity, when you get sodium excited, it releases yellow light. Thus this question. It says the yellow light given off by a sodium vapor lamp used for public lighting has a wavelength of 589 nanometers. What is the frequency of the radiation? You now have a minute to solve this. You guys good? If you all are typical, when you're done, more than half of you will have got this wrong. And for those of you that did get it wrong, you got it wrong for the same reason that you got 2 questions wrong on the previous test. On the previous test, you tried to take kilojoules and joules and jam them together, and you found out that don't work. So typically it will convert joules to kilojoules by dividing by 1,000. Guys, what are the units that you're trying to jam together now? Nanometers and meters. So guys, allow me, and feel free to just do away with what I'm about to suggest. You can make this as hard as you want. But guys, in the same way that I suggested to you that it's easier to convert joules to kilojoules because you end up with more reasonable numbers, guys, one of the things that we need to learn to do in this class is do things in ways that cut down the space for mistakes. And I find it's way easier for me to deal with joules into kilojoules because there's neat little decimal numbers. When I convert joules or kilojoules into joules, I got all sorts of zeros, and that's a mess. Same thing here. So guys, solving this problem, we've got C is equal to lambda nu. That's not nu. C is equal to lambda nu. Then guys, we need values. Remind me what's on the AP sheet for speed of light. Is it 2.9 something? Okay, so it's 2.98 what? 2.998 times 10 to the 8th meters per second. Then guys, we are solving for frequency, so the second thing will be our x. We need to know the wavelength. We know that it's 589, but that's nanometers, and we got to convert that to meters. Now guys, not many of you would suppose to convert meters into nanometers. That's ridiculous. But let me show you the easiest stinking way to convert nanometers to meters. Nano means 10 to the negative 9th. That's all you got to do, is add 10 to the negative 9th to this thing, and you're out the door. Now, some people go, wait, that's not in proper scientific notation. Shouldn't I move the decimal over 2 places? You can, but you're going to screw it up. Just do this and you're done. And then this is times x. Now, guys, look at the mathematical magic. Meters cancel. What are you left with? Inverse seconds. We call those hertz. Those are the units for frequency. So let's do the math. So 2.998 times 10, 2.998 times 10 to the 8th, and we're going to divide that by 589 times 10 to the negative 9th. And what do we get for significant digits? Like 3? I see 3. So I'm going to go 5.09 times 10 to the 14th hertz. Yeah? We okay? I did what? Oh, yeah, right. Oh, I see. Yeah, I see what you're saying. Yeah. I got you. Hey, so guys, keep these numbers in mind. Ready? 589, and let's just round that bottom number to 5 times 10 to the 14th. 589, 5 times 10 to the 14th. Now, guys, watch this. Do you see it? What was our wavelength? What was our wavelength? No, that's frequency. What was our wavelength? 589 nanometers. Guys, notice the units for this are nanometers. So here's 500. So this is 550, 60, 70, 80, 90. So 589, somewhere in this region, which is yellow. Then we come up here to frequency, and our frequency was 5-ish, right? Times 10 to the 14th, which interestingly is right between 10 to the 14th and 10 to the 15th, and it places us right in there, which is right in there, which is the same stinking thing. So, guys, are you ready for something amazing? Your eyeballs. Your eyeballs have the ability to see almost an infinite number of colors, regardless of what Apple and Steve Jobs tries to tell you about their retina displays. You know about that, right? They tried to say that their displays could create more colors than the eye can see. Anyway, doesn't matter. But guys, how does your eye do that? And the answer is your eyeball is a light energy detector. So what's the difference between all these different forms of light? They just have different wavelengths and frequencies. We'll relate that to energy in a minute. But guys, your eyeballs can distinguish such small differences in wavelength and frequency that we can take this very, very narrow bit of the electromagnetic spectrum and turn it into an almost unlimited number of colors. And it's simply because your brain is able to tease apart these minute differences in frequency and wavelength. That to me is a miracle. It's stinking amazing that we can do that. Guys, fascinating stuff. How we doing? You guys okay? All right. So guys, we are now going to shift gears. This is a big shift. So any questions about waves and frequency and wavelength? Feeling good? Okay. So guys, now we're going to make the tie back. I wish there used to be an easier way to do this. Hold on. That's not it. That's it. Okay. So guys, we are now going to connect this to the structure of atoms. Please write down this important term that you've never heard of before. So guys, this is subtle, but this is amazing. So here's where we are right now. Yellow light. Let's just focus on yellow light. What is the wavelength of that yellow light? 589 nanometers. What is the frequency of that yellow light? 5 times 10 to the 14th inverse seconds. But guys, we can now answer another question. What is the energy of that yellow light? Is it high or is it low? What's low energy light? Red. High? Violet, right? Purple, violet, whatever you call it. So red, orange, yellow, green, blue, indigo, violet. So is it shifted towards the low or the high energy side? The low energy side, right? And so this is how this thinking then goes. Imagine that you're standing, if you will, under that sodium vapor light. And you understand, guys, right, that sodium vapor light is streaming out of that light. Amazingly obvious. And as that light is transferring from the bulb to your body, it is transferring energy. You understand that? You've experienced that when it's sunlight because, man, it gets you warm, right? Well, guys, that sodium vapor light is also transferring energy to you. But this is the interesting deal. Guys, if we could take that light from that sodium vapor light, and if we could measure the amount of energy that was being transferred, guys, what we would find is this. There's not an infinite amount of energy that could be transferred. It's not like there's 10 joules and 20 joules and 50 joules and 70 and 32. Guys, what we find is that light of a given color can only transfer energy in given values. Should we write that down? Let's write that down. Light of a given color can only transfer energy in given values. Light of a given color can only transfer energy in given or fixed values. So guys, let me give you an analogy. It goes like this. So if you're sitting underneath this sodium vapor light and you're literally soaking in the energy, guys, stop thinking of light as just this flow like water coming out of a shower head. Guys, that is not what light is like. Light is not like water coming out of a shower head. So what is it like? And the answer, guys, is it's a lot like bullets out of a gun. So here's the example. You realize this is just my excuse to shoot you guys with darts, right? But I would like to point out, they're whistle darts. Okay, so this then becomes the idea, Cade, you know I love you, but this is going to hurt. So guys, the idea is this. We are no longer thinking about light as a shower head. So guys, imagine instead that this is the sodium vapor light and Cade's out on the playground. So guys, this vapor light can now transfer energy to Cade. Safety first, PPE. Here we go. So guys, the idea is this. If I want to, if this light is transferring energy to Cade, it isn't just a stream of energy. Think of it like bullets. So let's give this a number. Say that this bullet of light has 1 joule associated with it. So how much energy did Cade just absorb? A joule. Now, 2 joules. Now, 3 joules minus a little bit that went into the table. But guys, this is then the question. Is there anything that I can do to this gun to transfer half a joule of energy to Cade? No. No, because it could be a different color of light, but if this is yellow light, and if yellow light, by the way, do you guys know the name for bullets of light? They're called photons. And so guys, the idea is this. So photons are little packets of light energy, and if yellow light has an energy of 1 joule per photon, that about got you in that little soft spot right there. Yeah. Guys, all I can do is transfer energy to Cade in multiples of 1 joule. There's nothing that you can do with yellow light to transfer energy that is, and guys, this is the important point. Hear this carefully. There's nothing you can do to transfer energy that aren't multiples of the energy of a photon. Does that make sense? So yellow light, darts, 1 joule per photon, all I can do is pump energy into Cade in multiples of 1. Now what if I wanted to do multiples of 2? Then I need light that's more towards the violet end of the spectrum. So not all light has the same energy, but if you've got a fixed color, then we know the energy of a photon, and all we can do is transfer energy with the multiples of that number. Does that make sense? So guys, that is the idea behind quantized energy. This was a really big idea, because what it says then is that if you've got a fixed color of light, that light has a fixed amount of energy. And all we can do is transfer energy in multiples of that fixed number. Guys, you ready for the big idea? Why? Why is it that if we've got a sodium vapor light, the energy that comes out of that sodium vapor light has a fixed amount or multiples of a fixed amount? Why can't that sodium vapor light just spew all energies all over the place? Yeah. Yes. Where's the energy coming from? Ultimately, where's the energy coming from? Falling electrons. So what does it mean that in an atom they can't just spew all energies? It means electrons cannot be in all locations. If electrons could be anywhere, then they could fall from anywhere to anywhere, and as a result, they could release all energies. But because there are places electrons can be, and there are places that electrons can't be, there are fixed places where they can go, there are fixed places where they can fall to, and therefore fixed amounts of energy that can be released. Does that make sense? Yeah. Yes. Yeah, and so that's where things get a little fuzzy, and that was the difficult switch from the Bohr to the Schrodinger model. Bohr envisioned these places as being these very tightly defined orbits. Schrodinger got us more comfortable with the idea that they're more like probabilities and orbitals. Now, the thing that's interesting is that if you get good enough spectroscopes, the ones that we have cost $5 and they're made of plastic, but if you get good enough spectroscopes, you can actually you can break out spectra to the point where you can actually see the difference in the energies of the electrons on opposite sides in the same orbital. It's really crazy. So guys, you ready for the big jumping off point? Do you still have your books open with me? Here's what we just said, looking in chapter 6. Here's what we just said. We find out that the energy that these atoms can lose only can happen in fixed amounts. They are quantized. Electrons can't be anywhere, they can't fall to anywhere, and as a result, we see fixed amount of energies being released from lights. Guys, let me ask you a question. Open up your books to page 211. Does the picture at the top of that page now make sense? Guys, this is the idea. Atoms are not like ramps. Inside the electron structure of an atom, if it were like a ramp, those electrons could be anywhere and they could fall back to anywhere, and as a result, atoms would release an infinite different quantities of energy. That's not what's going on. Guys, atoms are like staircases. If the floor is the nucleus, I can be here if I'm an electron. I can be here if I'm an electron. Because that's the case, there's only two different types of energy I can release. I can release that amount of energy. This one could be dangerous, but we're going to try it. I can release this amount of energy. I guess that was 2. And then this amount of energy, number 3. But guys, I cannot release an amount of energy associated with me hovering between. I feel like Mr. Miyagi. I can't release an amount of energy associated with me floating between the steps. Do you get the idea? And of course you understand that the energy that's released isn't because the electron goes into the nucleus, right? But guys, that's also true of atoms. These electrons can't be everywhere, they can't go to everywhere, so these things are quantized like the steps on a ladder. Does that make sense? So then guys, the only other question we need to answer is this. How much energy, you trusting soul, you took off your goggles. How much energy is actually in one of these darts? Because we know that it's obviously not a joule. That would be like life-ending. So guys, how much energy is in one of these darts? And the answer, guys, is this. There's an equation for that. This is going to screw things up, so I got to do it this way. And guys, this is the equation. This is all review of what we just talked about, photons, energy. Guys, this is the equation. Write it down. E is equal to h nu. No, h is not heat. So what is h? Well, guys, h is Planck's constant, which has a value of 6.63 times 10 to the negative 34th joule seconds. Like everything else that's on the equation sheet. And then obviously, guys, nu is frequency. So this is E is equal to h nu. So this then, guys, leads us to our final question. You got the equation? Here's the question. Calculate the smallest increment of energy, the amount of energy that a bullet has, if that bullet is a photon of yellow light with a wavelength of 589 nanometers. So guys, we need an equation. Thankfully, we have one. E is equal to h nu. But you'll notice that the value that we need is nu, but they give us the wavelength. So what do we have to do with wavelength? Convert it to frequency. We already did that. It's 5 times 10 to the 14th. Huh? So now, how much energy does a yellow sodium vapor light photon have? Well, we need Planck's constant. I don't remember it. 6.626 times 10 to the negative 34th joule seconds. And then we need to multiply that by the frequency. We did better than 5, right? What was it, 4? 5 what? Thank you. 5.04 times 10 to the 14th inverse seconds. Notice that the seconds cancel and we're left with joules. So we do this math. 6.626 times 10 to the negative 34th, and then 5.04 times 10 to the 14th. Multiply those together. And guys, the value is 3.34 times 10 to the negative 19th joules, which I think you would all agree is significantly less than 1. It was just easier to talk about 1. Now guys, please understand, this is only true for that yellow light, right? All different colors, frequencies, and wavelengths have different energies associated with them. But then guys, if you think about it, look at how this changes. Gamma rays have a frequency on the order of 10 to the 20th. We're starting to close in on 1 joule per photon. Do you see that? That's why gamma rays are so destructive. Way, way, way high energy. Radio waves, guys, their frequencies are on the order of 10 to the 4th. Then you've got really on the order of negative 30th joules. So low energies there, and then all the shades in between. But guys, this then provided that connecting point for us to structure. Because when we found out that atoms can't release infinite amounts of energy, it then made us realize that the electrons are ordered into shells. Maddie, you're exactly right. Those became orbitals eventually, energy levels. We'll get there later, but that's the connecting back. So guys, we're done. Anything about any of that you want to explore? Was it too nerdy? Appropriately nerdy. It's kind of a descriptor for my life. You guys good? Okay. So this then is what we're going to do for Monday. Oh, look, the ramp and the ladder. Oh, and there's your homework. Guys, we're going to take a break. When we get back, we're going to jump into lab.